Let's wrap up section 2.4, the section on group action. We've got, I think, 4 more results. We're still pulling corollaries off of theorem 2.4.5. Recall, this told us if group G acts on set S, then this action induces a homomorphism mapping between group G and the group A of S. The group A of S being the group of all permutations of set S. So we'll repeatedly in the remainder of this section refer to the homomorphism induced by the group action. It's that homomorphism of theorem 2.4.5. A quick comment in terms of a group we've encountered before, the automorphism group of a given group. Recall, if G is a group, the set of all automorphisms of G, that is the set of all isomorphisms of G with itself, forms a group. And that group is denoted the automorphism group of G out G. This was brought up back in section 1.2 when we were still initially encountering groups. It's one of the exercises. Corollary 2.4.7, again, a corollary to that theorem 4.5, says let G be a group if we take an element of group G, lowercase g, conjugation by that element induces an automorphism of group G, and there's a homomorphism mapping group G into the automorphism group of G, whose kernel is capital C of G, that's all elements lowercase g in group G, such that Gx equals Xg as X ranges over all of group G. We probably in homework exercises encountered this C of G set before. Actually, it's called a center. Let's look at the next definition before we go through the proof. This set C of G is called a center of the group. It's all elements in the group that commute with everything else. So it includes the identity for sure. Here we're showing that that center is the kernel of a homomorphism. So that'll tell you it's a subgroup. That'll actually tell you it's a normal subgroup. Kernels of homomorphisms are normal subgroups of the given input group G. And this permutation that we're going to introduce in part 1, this automorphism of group G is referred to as the inner automorphism induced by element G. As we'll see, what this automorphism will denote at tau sub G, what this automorphism will be, is a mapping of X in G to the element Gx, G inverse in group G. So it takes an element of the group and it conjugates it by element G. That's what tau sub G does, as we'll see, but there's a name for it, inner automorphism. The second part deals with the center of the group, and let's go through the proofs. All right, part 1, claim is conjugation by G induces an automorphism of the group. Likely something we could have dealt with earlier. Here we're going to deal with it from a perspective of group action on a set. So group G, group capital G, let it act on itself by conjugation. So we're treating the group as group G, and we're treating the set on which it acts as the elements of the group as well. We've just happened to have a binary operation sitting around that we can use to define the group action. So what we're doing then is defining a mapping tau sub G of group G to itself, such that tau sub G of X is Gx, G inverse, as mentioned. So we're using conjugation and element G to define a mapping. Certainly it's a mapping from G to itself initially. So the action is conjugation. That gives us something in the setting of group action and lets us quote some results from chapter 2, section 4. This mapping is a bijection, as we saw in the proof of theorem 2.4.5. The group action determined a bijection. Here, the group action is conjugation. So something a touch more general in theorem 4.5. But for us, the group action is conjugation. So we do get a bijection. Next, if we'll take any two elements of group G and apply tau sub G to the product xy, that'd give us, since we conjugate element xy by G, that'll give us G, xy, G inverse. We can stick an identity in there between the x and the y, a G inverse G version of the identity. And hey, Gx, G inverse, well, that's what tau sub G does to x. The second part, Gy, G inverse, that's what tau sub G does to y. So we've established that tau sub G of xy is tau sub G of x, tau sub G of y. That tells you tau sub G is a homomorphism. We just observed that it was a bijection, one-to-one and onto. A one-to-one and onto homomorphism is an isomorphism. Yeah, well, an isomorphism of G with itself is also called an automorphism. So this tau sub G is an automorphism of group G induced by element G, if you like. So that takes care of the first part, using conjugation to define automorphisms. Second claim is now a mapping from group G into the automorphism group and behavior of the kernel of that. So for part two, let G act on itself by conjugation. Again, same group action. We saw that there's a homomorphism, the induced homomorphism mentioned in theorem 4.5, that maps group G to this A of G, the group of all permutations on set G. So here's the homomorphism. This tau is induced by the conjugation action. So for G, an element of the group, okay, look how the mapping goes. Things are picking up in difficulty a little bit. We've got a mapping from group G to this group of permutations. And we've also got permutations out there. So there's mappings from different places. Tau maps G to a permutation. So for G, lowercase g, and group G, tau of G is an element of capital A of G. In other words, tau of G is a permutation of G. And that permutation maps X in group G to Gx, G inverse, because the group action is conjugation and the homomorphism is related to the group action. The homomorphism, tau, is related to the group action. We want to show the kernel is the center of that group. So take something in the kernel of tau. All right, here's what that means. Tau maps elements of the group to permutations of the group. So the kernel is the stuff mapped to the identity. We need the identity in this group of permutations. That'd just be the identity mapping on set G. So if G is in the kernel of tau, then tau takes G to the identity mapping on set G. That's what the kernel is by definition, and that's what the identity is over here in the codomain of that mapping. But I know what tau of G does to elements X of G. It takes X to Gx, G inverse. Well, the identity, 1 sub G, as Hungerford denotes it, takes X to itself. So if G is in the kernel, we know tau of G is the identity on set G. Tau of G takes elements of G, X, and maps into Gx, G inverse. Well, if that's the identity, those must be equal, and this must be valid throughout set G for all X and G. So we need Gx, G inverse to equal X, provided G is in the kernel of the induced homomorphism. But if Gx, G inverse equals X for all X and G, we could multiply this little equation on the right by element G to produce Gx equals Xg. And that tells you we've got an element of the kernel. Also, if we have an element of the center, then we can multiply both sides on the right by G inverse to produce this equation. That is, we get G is in the kernel if and only if G is in the center. We get the equality of those two sets. So the kernel of tau is the center of G. Back to the notes. We've already pointed out the terminology center of G and the inner automorphism. We had encountered the class equation. I guess it was Corollary 4.4. So we can modify that a little bit given the new information. The center of G is a normal subgroup. You can see by the definition or the fact that we just showed it's a kernel of something or other. If we have an element of the center of G, then G equals XG, X inverse for all X in G. So if we wanted to look at the conjugacy class for G, if we take it and conjugate it by any element in X, you simply get G back. Conjugacy class of G consists only of G itself. So if we're dealing with a finite group and we take an element of the center of that group, then Corollary 4.4 part 1 told us that the cardinality of the conjugacy class, and when we choose something from the center, that cardinality is 1, as just observed. The corollary tells us that that equals the index of the centralizer in group G of X, the index of the centralizer of group of X and G in group G. This square bracketed quantity equals the cardinality of the conjugacy class. But hey, when you choose something from the center, that cardinality is 1. So that's where we get this from. So in light of these centralizers of elements, we got special ones. And the special ones are when we take X values from the center of group G. Those indexes are just 1 in that case. The class equation from Corollary 4.4 part 2 was for finite group G, the cardinality of G is the sum of the index of centralizers in group G, where we've summed over representatives of the conjugacy classes. They're equivalence classes. That's when they have bars over them as well. If we had n equivalence classes, n conjugacy classes, we'll take n representatives, and that's what the class equation stated. Well, we can modify that a little bit in light of this center thing. A bunch of these are 1s. Well, every time we choose an x sub I in the center of G, we're getting this index to be 1. So what we could do is pull off from the summation all of the 1s. How many of those 1s are there? Well, there's one of those indexes is 1 for every element in the center of G. Remember, these represent cardinalities of equivalence classes, these indices, and they're just cardinality 1 if we choose an element of the center. So we can pick those off one at a time. There's a total of, however big the center of G is. There's a total of cardinality of center of G 1s here, and whatever's left over. So what we then get is a sum, say, from I equals 1 to m of the remaining indices, where all these remaining indices are of cardinality strictly greater than 1. Arguably, I might need to re-index from this summation to that summation. So we haven't gotten into that level of detail. But we can certainly deal with expressing the cardinality of G as the cardinality of the center plus the sum of these indices. This summation here being taken over all I, where we have conjugacy classes x1 bar through x sub m bar, and each of these conjugacy classes is larger than 1. In other words, the index of the centralizer is strictly greater than 1. So just a little alternative take on the class equation. And we got 3 more results. just go through and state and prove those. The third of which I say sort of foreshadows the next section, and we're interested in group action because we're interested in the CELO theorems. So we'll make a comment before that. Otherwise, let's just look at proofs. Proposition 2.4.8 states, let H be a subgroup of group G, and let G act on set S of all left cosets of H and G by left translation. Okay, it's group action on a set, the set of left cosets of H. Quick little comment, left translation would be taking a left coset of H, say X times H, where X is some group element, and left translation by a group element, we'd take maybe lowercase g, and we'd multiply on the left coset by g. So we'd take left coset xh to left coset g times xh. That's what left translation means. And we'll have the symbols. They're coming, and I see them in the shadows from here. The claim is the kernel of the induced homomorphism, mapping G to this group of permutations, is contained in H. So we're getting a kernel contained in a subgroup using group action. All right. G acts on set S of left cosets by left translation. The induced homomorphism from theorem 4.5, wasn't it? Maps group G into the set of permutations on that set. It'll map element G to the permutation of the set of left cosets of H. Let's denote that tau sub G, similar to what we used in the past. It takes left coset XH, applies left translation to it. That is, it multiplies on the left by G. So we take left coset XH and map it to left coset G XH or GXH. That is, tau sub G takes XH to G XH. More explicitly, we want to show that the kernel of the induced homomorphism from here to there is contained in capital H. It's a short computation, but suppose G is in the kernel of the homomorphism. We never gave this homomorphism a name from here to here. It is not the tau. It's the homomorphism induced by the group action promised to us by theorem 4.5. But anyhow, we have a homomorphism between G and this group of permutations. If G is in the kernel of that homomorphism, then G is mapped to the identity over here by that homomorphism. The identity in this group of permutations on set S is simply the identity mapping on set S. 1 sub S, as Hungerford denotes it. So we must have then that the mapping associated with element G, tau sub G, is the identity on S under the assumption that G is in the kernel of that homomorphism. So GXH must equal XH for all X in G. That is, when we've applied tau sub G to left coset XH, when we've applied tau sub G to left coset XH, we get GXH out. That's the left translation. But if G is in the kernel, that should leave XH fixed. So this should also equal XH because G is in the kernel of the unknown homomorphism, the induced homomorphism. So we get XH itself back out as well. So we get an equality of those two. This has to hold for all X in G. We've got mappings on the set of cosets. That's where this last little comment comes from. If we take X to be the identity, say, plug in X equals the identity, we get G times the identity H. Of course, that's G times H itself. That must equal on the right-hand side of this equation, the identity times H, which is H itself. So GH must equal H. but that implies G is an element of H, equality of cosets. And we just showed if G is in the kernel of the induced homomorphism, then G is an element of H. That is, the kernel is a subset of this subgroup H. And that was the claim. Kernel of the induced homomorphism is contained in this group H. So this is giving us locations of kernels. That is a touch more useful to this result, which is going to look a little familiar. This is new stuff, but it reminds me of Cayley's theorem. Corollary to that previous result is if H is a subgroup of index n in group G, of course the index tells you the number of cosets in G, left cosets say, then, or excuse me, and no non-trivial normal subgroup of G is contained in H, then G is isomorphic to a subgroup of S sub n. But didn't Cayley's theorem tell us every group G is isomorphic to a subgroup of a symmetry group? If G is a finite group, then it's isomorphic to a subgroup of S sub n. Yeah, but we didn't say G's finite here. It must be. I mean, look at the conclusion. It's isomorphic to a subgroup of a finite group. So it must be that G is finite, but that wasn't hypotheses going into this. Hypotheses were the stuff about a subgroup of index n and something about locations of normal subgroups. No non-trivial normal subgroup of G is contained in H. And we just saw something about where some kernels of homomorphisms are located. So this reminds me of Cayley's theorem. It's not Cayley's theorem. The hypotheses are a bit more stringent than they were for Cayley's theorem. Cayley's theorem could draw this conclusion simply by having G as a finite group. We don't have that hypothesis, but we do have that conclusion. Okay. So let S be the set of all left cosets of H and G, so we can apply the equipment we have about group action as relates to that setting. Let group G act on the set S by left translation. It's the same thing we did in the previous proposition, 4.8. That previous proposition tells us the kernel of the induced homomorphism mapping G into the group of permutations is contained in this subgroup H because we've chosen the group action to be action of group G on the set of left cosets of H. That's the setting that allows us to draw this conclusion. The kernel of any homomorphism is a normal subgroup. Theorem 1.5.5 told us kernels of homomorphisms are themselves normal subgroups of a given group. Again, here's the input group, here's the output group of the induced homomorphism, but we never gave the induced homomorphism itself a name. So the kernel of that mysterious induced homomorphism is a normal subgroup of G, and we know it's contained in H by the previous result. But we've hypothesized something about normal subgroups contained in H. We've hypothesized that no non-trivial normal subgroup of G is contained in H. But we've got the kernel of the induced homomorphism is a normal subgroup contained in H. Well, it must be that H is the identity. It must be the trivial normal subgroup by hypothesis. So we've got that the kernel is contained in H. It must be simply the trivial subgroup. But wait, when kernels of homomorphisms are trivial, those homomorphisms are one-to-one. Theorem 1.2.3, something we saw early on. So we've established that the induced homomorphism must be one-to-one as well. So it's a one-to-one homomorphism. It's a monomorphism. How are we doing? We're trying to show G is isomorphic to a subgroup of G sub n. Well, we got ourselves an isomorphism here. We've got a one-to-one homomorphism. Mapping this into that, okay, well, it'll be onto whatever its image is. So G is isomorphic to some subgroup of the group of all permutations on the left cosets of H, of which there are n left cosets. I mean, that was hypotheses. So one-to-one homomorphism, it's onto its image. Mappings are always onto their image. I don't know what the image is exactly, but I know where it is. It's in this group of permutations. But set S was of cardinality n. Set S consisted of left cosets of H, and we said the index of H and G was n. So that's how many left cosets there are. So this permutation group, this A of S group, is isomorphic to S sub n. G is isomorphic to a subgroup of A of S. A of S is isomorphic to S sub n. So G is isomorphic to a subgroup of S sub n. So there's actually a moderate amount of equipment used here. We've used the information about group action and all the way back to normal subgroups as they relate to kernels and trivial kernels implying one-to-oneness, implying injectivity monomorphisms. And one final result from this section. This is the result I claim foreshadows the results in section 2.5 on CELO theorems. It deals with, well, doesn't deal with a subgroup, existence of a subgroup, but it deals with a group of a certain order. In that sense, it reminds me of the CELO theorems. The statement is, if H is a subgroup of a finite group G of index P, okay, similar to what we had before, except this time the number of left cosets of H and G is P, before it was N, where P is the smallest prime dividing the order of G, then H is normal in G. Okay, I said this involves or relates to a group of order P. It's not a subgroup of G though. We've got if we've got H normal in G, then we could look at the quotient group G mod H. That'd be the group of left cosets of H, of which there are P. So there's your group of order P. It's G mod H that's a group of order P. When we deal with the CELO theorems, we'll be finding for prime divisors of the order of a group, we'll be find subgroups of that prime order and more. But in the sense that we're dealing with prime divisors of the order of the group, in that sense, this reminds me of the CELO theorems, foreshadows them. All right, so we're trying to show this subgroup H under certain conditions is normal in G. Okay, well, let S be the set of all left cosets of H and G, as we've done in this video. The set of all permutations of S, A of S, forms a group. That group's isomorphic to S sub P. Because there are P left cosets of H, that's index P hypotheses up there. Same thing we had in the previous proof, except this time we've got P is a parameter. Last time we had N. If K is the kernel of the induced homomorphism mapping G into A of S, again, not giving that a name, but knowing it exists ultimately by proposition 5, I think it is. Then the kernel of that homomorphism is normal in G. As we've seen, kernels are always normal. It's contained in H, as was shown in the proof of proposition 2.4.8. So we've got a normal subgroup of H. Now consider G mod K. Furthermore, let's see, so K is the kernel of a homomorphism. Kernels of homomorphism are normal subgroups. We've got that covered. G mod K makes sense as a quotient group because K is a normal subgroup, because it's a kernel of something. It's a kernel of the induced homomorphism, whatever that is. So group G mod K makes sense. Hey, the first isomorphism theorem, Corollary 1.5.7, I guess it was, has something to say about this. It says if we have a homomorphism from one group to another, and we look at that input group G mod the kernel of that homomorphism, and that's what K is, we get something isomorphic to the image of that homomorphism, the image of G under the homomorphism. So G mod K is isomorphic to some subgroup of the group A of S. A of S is isomorphic to the more familiar symmetry group S sub P, because set S is finite. So we can conclude G mod K is isomorphic to a subgroup of S sub P. First, it's a subgroup of A of S, but A of S is isomorphic to S sub P. First isomorphism theorem. Group mod kernel isomorphic to image. I don't remember a lot of this stuff off the top of my head, but I remember the first isomorphism theorem only because we used it so much. Lagrange's theorem. It's been a while since we've seen that. Dealing with a finite group G. So Lagrange's theorem, I got to be very careful about, deals with products of cardinal numbers. Yeah, if everything's finite, I can talk division. So we've got finite groups, so divisors will make sense here. So Lagrange's theorem tells us that the order of G mod K, being a subgroup of S sub P, must divide the order of S sub P, which is P factorial. Also, every divisor of the order of G mod K, that is the index of K in G, must divide the order of G itself, because the order of G, also by Lagrange's theorem, is the order of K times the index of K in G. It's the size of that kernel times the number of cosets of that kernel in G, the index. So here's what we know about the cardinality of G mod K. It divides P factorial, and it also divides the cardinality of G. We didn't say too much about the cardinality of G other than it was finite, and something about P being the smallest prime dividing the order of G. And now we're talking about something dividing the order of G. And we haven't used that prime stuff yet, so that must be how we'll wrap it up. Okay, so here's what we have at the bottom of this slide that's relevant to the next slide. Cardinality of G mod K divides P factorial and also divides the cardinality of G, the order of group G. But no number smaller than P, except for 1, can divide the order of G. P is the smallest prime dividing the order of G was hypotheses. So we know G mod K, order of, divides G. But we can't have an order, prime order, smaller than P that divides G. We can have a composite order either, because that'd be made up of smaller primes. So we're left with the options that the order of G mod K is either P or 1. P is the smallest prime dividing the order of G. We've got G mod K dividing the order of G. All right, then it's got to be either P or 1. Couldn't be a smaller prime, couldn't be a smaller composite number either. We want to draw the conclusion, actually, that it equals P. But we haven't tied it down yet, but we can draw this conclusion about the order of G mod K being a divisor of the order of G. Now, G mod K, that is a group of order, index of K and G, right? It's a quotient group. Its elements are left cosets, say, of a normal subgroup K. How many of those are there? Well, that's what the index symbols represent, the number of left cosets of K and G. I keep emphasizing that when I state these things. And Lagrange tells us, okay, so we had H is a subgroup of G. We argued above that K is a subgroup of H, coming from a previous result. So we've got these 3 levels of groups. G is a big group, H is a subgroup of G, and K is a subgroup of H, the middle group. Lagrange tells us that we can write the index of the little group and the big group is the product of the index of the middle group and the big group times the index of the little group and the middle group. If you can divide, this is a lot easier to remember. And you can, because we're dealing with finite groups. Lagrange says it in terms of products of indices, products of cardinal numbers. But we can interpret in terms of divisions of nice little finite cardinalities. So we get this index in terms of the product of these 2 indices. But this index is a number of left cosets of H and G. We've assumed that index is P. H is a subgroup of G of index P. That is, there's P left cosets of H and G. That parameter is P, so we pick up a P right there. We're left with the index of K and H. Well, it's at least 1. So we get the order of G mod K is greater than or equal to P. But we knew it was either P or 1. Must be P. 1's not prime. So if that's the case, this is actually an equality. And if that's the case, this index must be 1. The index of K and H must be 1. So we draw the conclusion that the order of G mod K is P. We also draw from that string of equalities and inequalities that the index of K and H must in fact be 1. But wait a second, if the index of K and H is 1, that means H and K are the same thing. Yeah, K was a subgroup of H. Turns out it wasn't a proper subgroup, though. It equals H itself. H and K are the same. What are we trying to show? H is a normal subgroup of G. Cool. H equals K. You know K is a normal subgroup of G. It was the kernel of the induced homomorphism. So H itself must be a normal subgroup of G. And that takes care of the last result from this section. Back to the notes, I suppose. It takes care of everything from this section. So what's up next in section 2.5 is some applications of this group action stuff to CELO theorems. The CELO theorems proofs we'll give are quite similar to what you'd see in a senior level class. I'll point out when they overlap with my favorite senior level algebra book, the Fraley book, and they overlap largely with that. But I'll see you in the next video, next episode, and we'll do CELO theorems in section 2.5. Have a nice day.